Let's look at this problem right here. This is called Chebyshev's equation of order 1, and we're given two parts. First, we're asked to show that y of x is a solution to this differential equation, and the second part is to use reduction of order to find a general solution. Now, this is a special differential equation with a lot of information to cover, so that's why I chose this problem. I think it's a good review. So let's get started. First, let's verify that y of x is indeed a solution. So this should be quite easy. Y of x has derivatives y prime is equal to 1 and y double prime is equal to 0. So let's plug it into the left side of this differential equation and see what we get. 1 minus x squared times, well, y double prime is equal to 0, minus x times y prime is equal to 1, plus y is equal to x. Well, what happens? Multiply by 0 and we get 0. Multiply by 1 and we get just x, minus x, plus x. Everything cancels out and we get 0 as desired. So this is part A. We've shown that y of x is indeed a solution. And now, let's move on to reduction of order. So let's first do a little review of what reduction of order is. Basically, we have a theorem. We know that for any second order linear homogeneous equation like this, we know that it's linear because these coefficient functions are functions of x, and the derivatives of y are not involved in any more complicated forms than just this linear form. It's homogeneous, is set equal to 0. So we know that there are two linearly independent solutions. So what does that give us? Well, we know that when we have two linearly independent solutions, let's call the second solution that we're looking for y2. We know that if we have two linearly independent solutions, y2, and the first one is x, then the ratio is going to be non-constant. So the ratio is going to be another function of x. Let's call it u. So working off of this, we're going to look for a function of x, y2, which is in the form u times x. And now we can take derivatives of y2, plug it into the differential equation, and see what we get. So let's do it right here. We take the derivative of y2. First derivative of y2, you have to use the product rule. So first take the derivative of u, and we get u prime times x, plus take the derivative of x, which is just 1, we're left with u. Now let's take the second derivative. Use the product rule again over here on u prime, and we get u double prime times x, we leave that. Then we take the derivative of x, and then we get u prime, and then we take the derivative of u, which is also u prime. Then simplify, we get y2 double prime is equal to u double prime x plus 2 u prime. And now we're going to plug these values into our differential equation in order to see what we get for u. So we have 1 minus x squared times u double prime x plus 2 u prime minus x times u prime x plus u plus ux. This should be equal to 0. So let's collect terms. Let's collect terms by the derivatives of u so that we can get a differential equation in terms of u. So for u, let's distribute out the 1 minus x squared over here, and we should get x minus x cubed times u prime plus, let's get the coefficient of u prime, and we're going to do that by distributing this, which will give us 2 minus 2x squared, then minus x squared, u prime, and then for u, if we look over here, we get minus ux, and then plus ux, and you can see that that is going to cancel. So let's move on. Now we're left with x minus x cubed u double prime plus, gather these together, 2 minus 3x squared u prime is equal to 0. And now we're going to make a substitution. We have u double prime and u prime, so let's let w equal u prime, and then w prime is going to be u double prime. So you can see that this is where we get the name reduction of order. We make the substitution, which gives us a first order differential equation. So we take the second order, we take it down into a first order. So we have x minus x cubed w prime plus 2 minus 3x squared w is equal to 0. So how do we solve this? Well, we can see that this is separable. So let's bring this over to the other side, and let's call this w prime. We can rewrite this as dw dx is equal to the negative of this. So let's just invert this coefficient. The negative of this would be 3x squared minus 2 w. Then let's collect the like variables. So we get dw over w is equal to 3x squared minus 2 over x minus x cubed dx. And now to solve for w, we're going to have to integrate both sides. So how are we going to integrate this? Well, if we look at this, we have a rational function with polynomial on top and a polynomial on the bottom. So what this suggests to us is that we are going to need partial fraction decomposition. So let's go over that. (3x squared minus 2 over x minus x cubed). Now remember, we wanted to integrate this, and this is not going to be easy to integrate. So we're going to divide this fraction into sums of reciprocals of linear factors. So I'll show you how it works. We know that this is equal to 3x squared minus 2 over x times 1 minus x squared. And this is going to be equal to the sum of a over x plus bx plus c over 1 minus x squared. Now, if you look at this, we're actually doing something a little clever. So we see over here that we have 3x squared minus 2. This only has a quadratic term and a constant term. Over here, we know that we can factor 1 minus x squared into 1 plus x, 1 minus x, and then we can have basically three variables that we need to solve for. But in this case, it suffices to only have 2 because we're only solving for 2 in the end. So what we're going to do is there's not going to be an x term. So this c times x that we know when we multiply by the common denominator is going to disappear. So let's get rid of this c. It's a bit of a clever trick. So because you see now that we have a times the constant times the quadratic term, bx times the x, and the c disappears because we don't need an x term over here. And if you try doing it the other way, you'll see that it'll eventually be equivalent to this anyway. So this is just a little shortcut with a little foresight. So let's continue onwards. Basically, when we know that these two functions are equal, we're going to multiply by the common denominator and see what we get on the right hand side. So what that looks like is a is going to multiply by 1 minus x squared, bx is going to multiply by x, and it's going to equal this top numerator polynomial over here. So let's do it. 3x squared minus 2 is equal to a times 1 minus x squared plus bx times x. And we know that if we collect the powers of x and into basically a polynomial form, we get negative a plus b times x squared and then plus a. So equating the coefficients of each term, the powers of x in this polynomial, you get a very, very simple system of equations. Negative a plus b is equal to 3. A is equal to negative 2. A being negative 2 makes this a lot easier because we know that negative a is going to be 2 plus b is equal to 3. Subtract 2 from both sides, and we know that b is equal to 1. So this whole technique over here, partial fraction decomposition, gives us a way for us to integrate this intimidating looking rational polynomial function thing over here. So we got a is equal to negative 2, b is equal to 1. Let's move on to a different sheet of paper. So 3x over here, we're going to plug these things in. 3x squared minus 2 over x minus x cubed is equal to negative 2 over x plus 1 times x, so that's x over 1 minus x squared. And this is going to make our, this is integral of dw over w to this. It's going to make this part a lot easier. So let's continue moving onwards. Plugging this back in, well, we know that the integral of this integral is going to be equal to the ln of the absolute value of w. And this over here, when we substitute in what we got, a result of our partial fraction decomposition, gives us this. And now this is much easier to integrate. This gives us negative 2 ln of x. And you see conveniently we have just a linear x power. And then on the bottom, if you do the u substitution, you can kind of do it in your head. You know that the derivative of this is going to be negative 2x. So let's divide out the negative 2. You get the ln of 1 minus x squared, and then add plus c. Now this is where our assumption is going to be very important. So the reason that we have this assumption is so that it makes our absolute values and everything much simpler. So let's do that. When we have that the absolute value of x is less than 1, then we know that x squared is going to be also less than 1. So we know that what's inside here is going to be basically positive. So we don't need that absolute value. So let's look over here. ln of, well, using the rules of logarithms, you can take this power up there and we get ln of x to the negative 2. The absolute value disappears because when you square, it will be positive anyway. And then minus ln of, again, we take this to be positive using our assumption. So when we raise that to the power of a half, we take the square root essentially. Plus c. So now let's proceed. Let's raise both of these. Let's raise e to the power of both of these. That will give us absolute value of w. And now e to the power of this is going to be, well, we're going to take the e to the c out first, so that's our constant multiplier. And then we're going to use powers of rules of logarithms to convert this into a more easy expression. E to the ln of this is going to be, you take this negative in and then you divide it, and then x to the negative power, you divide that too. So you get basically 1 over x squared times 1 minus x squared. This is actually pretty nice looking. And then we're going to say that this is equal to some c, let's say this is c1. Some c times, well, e to the ln, the inverse functions cancel out, and we get c over x squared times 1 minus the square root of 1 minus x squared. And this is where c is equal to plus minus, well, plus minus when we remove the absolute value of this. So w is equal to that, is equal to this, plus minus e to the c1, or c equals 0, because you notice that if c equals 0, then w is going to equal 0, and that's going to satisfy what we had before. Let's see over here. It's going to satisfy what we had up here, so that's how we know up here. So that's how we know that we can have c is equal to 0. So basically we have this now. We have w is equal to this, and we know that w is equal to u prime, so we're going to be taking the integral of this. So how are we going to take the integral of this? Well, we're going to need another technique. So u prime is equal to c over x squared times the square root of 1 minus x squared. So the integral, this is du dx. So the integral of this dx is equal to the integral of this dx. Let's take out the constant c. And we know that this is going to be simply u. But how do we do this? Well, here, you might notice that it looks similar to some trig stuff that we did. So let's draw a little trig diagram, and the trig diagram should make things a little clearer. So here we go. Let's draw this right triangle. Let's call this angle theta. Now we're going to have here, well, we're going to put 1 as the hypotenuse and x over here. Again, we can do this because of our assumption. We know that the absolute value of x is less than 1. So that allows us to be valid by the triangle inequality. So here, if we have this, then by the Pythagorean theorem, we're going to have this side is going to be the square root of 1 minus x squared. So here, we notice that x is equal to sine of theta, meaning that dx is equal to cosine of theta d theta. And this gives us that square root of 1 minus x squared is equal to cosine of theta. So that makes this a lot simpler to express, equals c times the integral of dx is cosine of theta d theta, x squared is sine squared of theta, and the square root is equal to cosine of theta. Now we note that our cosine thetas cancel out, and we're left with this sine squared of theta on the bottom. Man, this is getting long. So let's move on. So now we're left with u is equal to c times d theta over sine squared theta. And now this is very Very easy. This is equal to sine squared on the bottom becomes cosecant squared theta. Oops, not an integral anymore. I mean, yes. Yes, it is an integral. It's a big integral. And then the integral of this, what I meant to say, is not an integral anymore, and we know that that's cotangent. So c times cotangent of theta, well, I guess plus another c too. So now, what do we do? Cotangent of theta, looking from our diagram up here. Well, we know that tangent is equal to opposite over adjacent, so cotangent of theta would be adjacent over the opposite. Square root of 1 minus x squared over x. And now we have our u. So finally we have u is equal to c times 1 minus x squared over x plus c2. If you remember all the way at the very beginning, we said that y2 is equal to u times x. So doing that will give us our final y2 is equal to this whole thing times x. The x cancels out here. C times square root of 1 minus x squared plus c2 times x. And again, we know that y equals x is a solution. So this is our whole thing, our general solution. Right here. So we cover some important techniques at the very beginning. Let's go through it. Reduction of order. This is reduction of order where we made this substitution. This whole thing over here. And then we solved for u by basically taking derivatives and taking product rules. Then we moved on to getting this thing, partial fractions. So we moved on and we eventually got to this, and we had to take a clever partial fraction decomposition to make this integral easier to compute. And then once we got that, then we ended up needing to integrate something like this when we plugged it back in. So for that we had to do a trig substitution, and in the end we get this. And since we've come this far already, I'm going to show you a little extra. So basically Chebyshev's equation is something that looks like this. 1 minus x squared times y double prime minus x times y prime plus a squared times y equals 0. So now you see why we called it order 1 in the problem. And the general solution to this actually has a very interesting form. It looks something like this. Y is equal to c1 of sine of a inverse sine of x plus c2 cosine of a inverse sine of x. This is a very interesting trigonometric form, and this can be solved by using series solutions, which converges in that under that constraint that we had given in the beginning. So here, well, we see that since the range of sine is from -1 to 1, the domain of the inverse should be from -1 to 1, so it makes sense. So let's show that this solution is equal to the solution that we got when a is equal to 1. So when a is equal to 1, then we get c1 times sine of inverse sine of x plus c2 times cosine of inverse sine of x. And when you take the sine of the inverse sine of something, the definition of inverse functions gives you just that input. So that's what corresponds up there. And here, c2, this is interesting. So the cosine of the inverse sine. Well, we know that cosine squared plus sine squared of x is equal to 1, which means that cosine of x should equal the square root of 1 minus sine squared of x. So cosine of this should equal, cosine of that should equal square root of 1 minus sine squared of the inverse sine of x. And as we saw again with the same rule, we get c1 x plus c2 times the square root of 1 minus x squared. So that's just showing that our solution that we got was a special case of something more special. And it also turns out that if we go beyond this constraint, then we'll end up in some, we'll end up with some complex, like literally complex stuff, like in the complex numbers, complex functions, and also we'll get inverse hyperbolic trig functions, and things look very interesting. Chebyshev equations are very interesting. So that kind of took a long while, but we did get to cover a lot of techniques, so that's good. This is our final solution, and thanks for watching.